So here are the official goals. I'm going to introduce you to the idea of dynamic modeling. Why do we call it dynamic modeling? Why is it so important? And we're going to talk about the SIR model family that Steve has already introduced you to as a tool for that, and talk again about some of the things that we learned from it. We're also going to demonstrate, we're actually going to create a model here today live, and I just want to stress that I have absolutely no reason for me to be nervous about that. So dynamic modeling is the idea of connecting processes that happen at the individual level, and usually individual events, like this foolish child reaching out to touch this wet-nosed child. That's an event that happens at the individual level, to population level processes that happen at a bigger time scale and over a larger period. So this is a very nice time series of measles reports from England and Wales. Steve has shown you similar pictures. And there's some key ideas here. Patterns like this emerge from individual events like this one. And it's really hard to understand those links. And dynamical models are the tool we use to do that. We ask if we have rules for what's happening at this level, what's going to emerge at a higher level. And if you're doing that, it's a dynamic model. And what we're showing you are some examples of dynamic models, but really the broad idea of dynamic models is the thing, and there's many ways to do that. And we'll be talking about a few, but hopefully giving you indications about a few more. So our SIR model divides people into susceptible, meaning they can get the disease, infectious, meaning they have the disease, and we're assuming, we're not differentiating. We're assuming either that everybody who has the disease is infectious, or we're assuming that we can average over that fact without losing too much detail in our model, or people can be recovered. And we're going to assume that people get better independently. So I just have a black arrow from I to R. If I'm in I, I'm on my own. I'm eventually going to travel to R. But this little blue arrow indicates influence. We assume people don't get sick, don't get infected independently, but instead are infected by contact with an infectious person. And that's what this blue arrow indicates. And this is a simple model that incorporates like the fundamental thing that makes it an infectious disease. And importantly, so one of the themes of this lecture is don't be afraid of differential equations. And there's two ways in which people are afraid of differential equations. One is they think that differential equations are big and scary, which they're not. I'm going to explain to you that you're not allowed to be afraid of them in that way. But the other way is they think that differential equations are better. There's this history in this field particularly of thinking that the differential equation model is the real model, and if you're doing something else, you should apologize for it. And that's basically wrong too. There's a lot of ways to make a dynamical model, and which model you want to use depends on what question you want to answer. And here, I'm going to claim I'm thinking about this model before I've even implemented it dynamically. I'm going to claim that this already gives us tools, even before I say exactly what my dynamical rules are. Just the fact that I'm assuming people get better independently but get sick while contacting an infectious person already allows me to ask questions like, if I run this model until the end, until things stop happening, what's the final result? And so let me ask you that. What would happen if I started a model like this, let's say with some people in S, some people in I, and some people in R? What's going to happen when it's done, when I'm done this process?
Is it acutely immunizing?
Is it acutely immunizing? Yes. I'm going to say that when people, I'm going to claim that I've sort of answered the question because people, when they're in I, they move to R at a certain rate, and I don't let them get out. If they were getting out of R, I would show you an arrow. And that's important. We try to use diagrams in this course in a structured way, and you are Catherine with a, is Catherine with a K also here? Darn it. And Kathleen is also here. So we're going to work on nomenclature. I was thinking we'd just call you C and UK and you Kath, but I'm going to let the three of you sort it out later.
So to answer your question.
Yes, please.
Well, I'm not sure if I can accurately, well, okay, given only your diagram.
Yes.
You will end up with a bunch of recovery.
Okay. So that may be true, and it would certainly be true if we didn't have this blue arrow, right? If there wasn't for this blue arrow, there's nothing to do when you're in S but move to I. There's nothing to do when you're in I but move to R. But with the blue arrow, what we find is, with the blue arrow, what we find and what Steve said, and it's pretty general, is that if there's not enough people in if there's nobody in I, you stop moving out of S, right? And so in general, you could wind up with everybody in R, but more typically, you would end up with some people in S and some people in R. And we can ask, based on this model alone, when does the disease increase and decrease? And I feel like I'm getting stuck on this slide, so I'm just going to say the disease is going to increase in general when we have more coming into I than going out of I, which is going to be, in general, if we have a lot of susceptibles, the disease is going to increase, and if we have fewer susceptibles, the disease is going to decrease. And this is a perfectly valid model, and you can even go further than this. Without constructing equations that you can simulate through time, you can analyze just the conceptual model, and that's important. The model is not the ODE. The ODE is one way to instantiate the model. And now we're going to talk about that one way to instantiate the model. So to actually make a model that we can simulate and ask how things are changing through time, we're going to need to make specific assumptions about how recovery and transmission operate in time. And the ODE is not something to be afraid of. It's not the only way to do it. It's not always the best way to do it. Conceptually, it's the simplest way to do it. You don't need a time scale. There's a lot of details that you have to worry about in any other model. The ODE is the conceptually simplest way to do it, but you may do it another way, either because you feel the other way is more realistic, or because conceptual simplicity is not the only thing you're worried about. On the spreadsheet, I'm going to make a discrete time model, which in some ways is conceptually more complicated, but in terms of actually putting it into a spreadsheet is a lot easier. And that can be fine, right? Our goal is to construct the model that's useful and good enough for the current application. There was a long, and I felt slightly disconnected quote from Einstein, which is frequently misquoted. But I like the misquote far better than the quote. The misquote is, your model should be as simple as possible, but not simpler. So, to instantiate the model, we're going to assume that infectious people recover at a constant per capita rate, just like Steve did. So it means it doesn't matter how long you've been sick, your instantaneous probability of getting better the next second is always a constant. And that rate is going to be, by per capita, I guess everybody knows what I mean, but I mean per person, right? So each person has an individual rate of gamma. So if we have I people in box I, then the total rate, the rate we're going to put into our population equation, is gamma times I. That's the rate in which people are moving out of box I. And the mean time that you're going to stay in the box is D. And these quantities have units. Gamma is a pure rate. It has units of 1 over time. D is the duration of infectiousness. It has units of time. Susceptible people, we're going to assume, get infected by going around and contacting people. So our conceptual model is that the susceptibles and the infecteds are all walking around, they're going to work, they're taking buses, they're shaking hands, and there's a certain rate at which they make contacts which are relevant to this particular disease. And what a contact is going to depend on what your disease is. For example, I just coughed, and now I'll shake hands with some of you. Of the people I contact, if I'm a susceptible, some of them are infectious, and of the infectious people I contact, some proportion of these contacts are going to be effective. So I'm going to define an effective contact exactly as a contact which will transmit the disease, assuming one of the people involved is susceptible and one of the people involved is infectious. And so the per capita rate at which susceptibles become infected is CP, it's the contact rate times this proportion of people that you meet who are infectious times this probability, and at the population level, that comes out to beta SI over N. Are you Jeanette?
Yes.
Okay, good. I was hoping you would, I can't see you in the light, but I was hoping you're here because a lot of this relates to the questions you asked at the lecture. Sorry, I have detracked myself. So this is the rate at which individuals are leaving, and this is, since it's, again, a per capita rate, we're going to multiply it by the number of people in the box to get our equation. I'm just going to say it's been conceptually useful to me to think about transmission from the other point of view. So we just talked about susceptibles walking around, meeting people, shaking hands, what's the probability? I'm now going to think about what if I wanted to focus on the infectious individuals? So they're walking around, right? I just coughed in my hand and I'm going to try to shake somebody's hand. We're supposed to cough in our elbows now, which is such a good idea. And it's only like in the last 20 years that somebody thought of that, right? Like I was taught as a kid to cough in my hand. Why? Why is that the right thing to teach a kid? Sorry. So infectious people go around contacting others at rate C. We're going to assume for now these rates are the same. Things get complicated if they're not. Some of these people are susceptible, and some proportion of these contacts are effective. It's exactly the same. And the interesting part is we get a per capita rate of infectious people infecting people, which is relevant to Steve's thing, are effective. But we can also scale that up to the population. And if our simple model is consistent, and it's always good to test yourself, if our simple model is consistent, that should give us the same answer we had before. We want to see that this way of calculating transmission from our simple conceptual model gives us the same answer as the other way. I'll mention, and I don't know if it's useful or not, these slides are already online, and there's also a set of handouts that's online. And some of you may want to check in the morning which lectures have handouts, because you can print out the handouts and scribble on them. You should not rely on the handouts. You definitely want to take notes, but it's very nice if you can just take notes on the parts that are going on in your brain, and you already have the handout as a, oh, there's a word I'm missing. Platform, no. Substrate. I don't know why that's the best word anyway. Since about last year, I often suddenly can't think of words, and it bugs me. Good. So now we've talked about the two key processes in our model and how we're going to estimate them for our ODE, and this is the ODE, and you are absolutely not allowed to be scared of it because it's absolutely dead simple. If I asked you to solve this ordinary differential equation, that's extremely hard. Like, I would not even want to solve this ODE, and you are allowed to be scared if somebody's trying to force you to solve an ODE. But if somebody's just showing you one as a way of explaining what they're doing, it's dead simple, and you have to not be scared of it. All this is saying is that I'm assuming each of these boxes are changing continuously and sort of adjusting their rate of change continuously, and this is the rate at which it's changing. So at any instant, the number of susceptibles is changing at this rate, representing the infections. At any instant, the number of infectious individuals is changing at this rate, which is representing the number of infections minus the number of recoveries. And that's all it means, and that's usually all you need to know about it. And I think that's one of the main themes of my lecture. And we're now going to construct a spreadsheet implementation. We're going to start as a discrete time model, and then we're going to talk about how it might link to an ODE. And we're just going to do it live, except that I have to record my screen. This is very exciting. Start recording, and no way to know if it's working. We'll just assume that it is. And then when I finish, I have to save it. That might be more important. So how are we going to construct this model? We're going to start by defining parameters. The parameters are the numbers that go, sort of the numbers that don't change, the things that are explaining the model. And I distinguish parameters from state variables. State variables are the things that tells you where your system is now. Those are the things that we're modeling the change of. So I'm going to start by saying beta. That sounds like it should be my first parameter. And if I write this, if I write beta is 1, I already feel nervous, like physically nervous. And can anybody tell me why? Does beta equal 1? Can beta equal 1? What's wrong with saying beta equals 1? To me, beta is a rate. Beta is the rate at which people are crashing around my population. It's a rate, it has units, and I really, really don't like ever saying beta equals 1 without knowing what units I'm talking about. I mean, that's how strongly I feel about units. It's going to come up on this slide as well. What's the other parameter we need to get started with this model? Gamma is correct. Did somebody else? And what's your name? Emmanuel. Gamma is absolutely correct, and it's so correct I feel bad for asking because I'm not actually going to write gamma. I'm going to write D because to me it's more intuitive, but it has exactly the same information as gamma, right? D is 1 over gamma, and I'm going to write D is days. D is how long I'm infectious, and I'm going to write a number for that. And so let us start coming up with some state variables. And actually now I'm going to make my first state variable time, which makes me think I need another parameter or pseudo parameter for now, which is delta t, which is how much. So what I'm going to do now is I'm going to follow my conceptual rules of these two processes, but I'm just going to go from time step to time step. And I said that having a finite time step introduces some small complications. What I'm going to do about those small complications is not worry about them for now. Typically, well, I think I've forced myself to jump ahead. If your time step is reasonably small, you typically don't have much to worry about. And that's one of the advantages of the ODE, is that you're logically taking your time step to 0, but in a way that you can actually solve it. And that's what makes the ODE the best thing. But it also means that you don't have to worry too much about discrete time models if your time step is small. And we'll also talk tomorrow morning, we'll talk about some of the advantages of having a discrete time step as well. So I'm going to delta t, and I'm going to make delta t1, which is potentially really dangerous. People very often make their delta t1, and then they forget that it's really a united quantity. And so it's important to remember that delta t is there, and to put it in wherever it logically belongs, whether it's 1 or not. And one of the things we should do, if we get this model working, is that we should experiment with changing delta t and make sure if we've set up the model correctly, it should only change our results slightly. Okay, so I'm going to start at time 0. What are some other state variables I want to have to fill in this model? Emmanuel again.
Well, the number of people in S, in I, and in R.
S, I, and R. And now I'm already upset with myself because I wrote time equals 0. We obviously can't do that. Control X, Control V, day. And as Emmanuel said, I'm going to denominate these in people. Oh, I just broke the spreadsheet. Control copy. Are there questions? I noticed people are looking uncomfortable. Maybe that's because we didn't have enough coffee, but.
Just, excuse me?
Yes.
Jeanette from University of Nairobi. If you just go back to the first column.
Yeah.
I just want to make sure that my understanding of D is the same. D is the rate at which people move from I to R.
D is the reciprocal of that rate. So I went over it quickly, and Steve also might have gone over it too quickly. D is 1 over gamma, and so D has units of days, whereas gamma has units of 1 over days. So if I'm sick on average for 5 days, I would say D is 5 days. Or if I was writing in terms of gamma, I would say gamma is 1 over 5 per day or something. Does that make sense? So D is the reciprocal of gamma. And I like it better because it makes more sense and it generalizes better. There's a history of mathematicians who say the rate is the real thing and the reciprocal is something you should calculate. But that's assuming that the ODE is a real thing. I don't think the ODE is a real thing. The ODE is an approximation, and the real thing is the average length of infectiousness. So thank you for that chance to pontificate. Yes?
Okay, John from Zimbabwe. So I was saying D is the infectiousness period.
Yes.
That's the way I'm understanding it.
D is the average duration of infectiousness. So a person is infectious on average for length D. We're actually going to come back and talk about how that plays out for an ODE model specifically. It may not be what you expect, but D is the average duration of infectiousness. And that is in the slides and the notes as well. So if you take a short note now, you'll have a chance to. So let's start with some susceptible people and some infectious people and some recovered people, And now let's ask what's going to happen to them. Okay, so what are the transitions in this model? What can happen to you if you're one of the people in one of my boxes? Thank you.
You can move from susceptible to infected.
Okay, that is correct. And I'm going to call that infection. Oop. Sometimes my touchpad just goes crazy, and I don't know why. So I'm going to turn it off, which will probably also make me crazy. Infection. And what are the units of this process of infection? Like, there's actually two different ways to do it. So I heard two different answers, and they're both right. Some people said people, and some people said people per time. I'm going to choose to think about it as people per unit time, because that's how the equations I'm used to. Okay, and other than infection, did you raise your hand? What's the other process?
Can move from infection to recovered.
Yes, and what is your name?
Susan.
Susan. Oh, nice to meet you. And so we'll call that recovery, and that also has units of people per time. And how would we calculate that? Sorry, how would we calculate? Yeah, let's calculate recovery first. That seems easier. So I now want to actually start calculating things. What's my formula for recovery? Well, who's recovering? It's the infectious people. And what's the rate at which they're recovering? 1 over D. That's right. So I'm just going to write this. Oh, but I'm not going to do that. So this is important. I feel it's important. First thing I'm going to do now is I'm going to give D a name. And I'm probably going to call it D. I've now turned off my touchpad cleverly. Oh, come on. Sorry. The computer always acts worse when it knows people are watching. So I'm going to call this D. Yeah, you see? I'm going to call that D. And now I have to go back here. Do I really need my mouse again? This is terrible. So the rate of recovery, I'm going to say it's equal to the number of infectious people divided by D. Okay, and I'm going to assume that worked because otherwise it should have given me an error. Okay, how about infection? What is the rate of infection in this model? Do people remember? Did anybody take it in their notes?
You need to multiply the susceptible by the infected.
Okay, I hear a lot of mumbling, but I'm going to choose to assume I heard the correct answer in there, which is first that I need to give a name to beta, so let's do that painstakingly with my finger. Come on. So I'm going to turn the mouse back on. I really apologize for this. So now that I have the mouse, can I add a range? Yes. We're going to call that beta. What else do I need or want that I don't have in order to make this? So N. Very good. Who said that? Thank you. So I'm going to make a column for N. There's different ways I can do N. So I want N to be constant, so I could have started by making that a parameter. But what I prefer to do is calculate N in the spreadsheet because it's another way to check myself. Just like I calculated transmission twice, I'm going to make sure N stays constant, and then I'm going to calculate it anyway. So I'm going to insert a column here, and I'm going to make it into N. And I'm going to denominate it with units because I'm crazy about units. And I'm going to say N is equal to the sum of these numbers. And how do I do that? With a dot or a colon? Does anybody know? Oh no, I should just select the range. That's what I should do. Let's try again. Sum of these numbers. Good. Okay, and now I'm prepared to say that this transition equals beta times S times, I over N. I feel like I'm happy with that. Okay, so these quantities are both 0. And why is that? Why am I not getting a disease? Yes, and I typically do this. I typically put my first infectious person in the recovered class instead of the infectious class, and I don't get good epidemics that way. Okay, so we're going to fix that mistake. And you are? Alan. Yeah, it's hard because I want people to pipe up, but I also want people to learn each other's names, or maybe I should just leave that to you. Okay, so good. So now we have transitions. That seems potentially good. How are we going to calculate our next row? Well, the first thing we want to calculate is our time for the next time step. How are we going to do that? Ha! That's what I was hoping someone would say. You fell into my evil trap. No, we're going to increase by delta t, which means we need to name delta t. So we're going to do that. Always embrace units and explicitness and all that stuff. So I'm now going to say this equals this.
I think you wanted to name cell 10.
Sorry?
I think you wanted to name cell 10. But
Oh, did I do it wrong? Okay. Yeah, that's pretty good. So what do I do now? It's not going to let me delete it because my screen is too big, or what? How do I delete it? The edit button's going to let me delete it? Oh, but I can change it. Fine. I still feel like I should be able to delete it, but that would be a terrible way to waste time right now. Okay, good. So how am I going to calculate S for the next time? Should we go back to the picture? Let's go back to the picture just for reference. So how are we going to calculate S for the next time? Okay, we're going to start with S. That's a good point, right? So the S for the next time is going to be based on S for this time. And what's going to change it? Well, maybe I shouldn't have showed you this picture. What's going to change it is the people who are leaving through this arrow, right? And what do we call that? It's not the number of infectious individuals, it's the number of infections, which is not what we call it. We haven't called it anything except the infection transition. So what I'm going to do is I'm going to write that this is S. No, I'm not going to write that. This is the cell above it, right? And we do that because it's going to be recursive, minus the rate of infection. Okay. And now I'm going to hit enter. I'm not going to hit enter. Why am I not going to hit enter?
Because you need to multiply by the same cell, D4.
I'm going to multiply it by D4.
Oh, sorry, by...
No, so I've already put the D4 in here. That's important, right? Any transition out of a box needs to have the people in the box in the transition, right? And that's a good check. So this equation here in H4 had better have D4 in it, which it does, or else I'd better be adding the D4 now. But that's, so I've already put the D4, I've already calculated the transition. Our hint is to look at the units. What are the units of S? People, and what are the units of transition? So I have to multiply it by something with units of time, and there's only one reasonable thing. Good. So that's that. And what about I? So I is going to be, I feel like I should speed up a little now. Are people ready for me to speed up a little? Do people have questions? So I'm just going to say I is going to be the number that was in I plus the infections minus the recoveries, and then times delta t. Is this big enough? Should I make it a little bigger? And somebody said it was okay, so I'm going to make it a little bigger anyway. And how about R? R is going to be the number in R plus the recoveries times delta t. And now we're very, well, and n, now we're excited, n is going to be equal to, actually all these things I want to copy down, right? And we're very excited because we want to see if n is 1,000. Okay, we did something right. So that's good. So this is possibly a dynamical model. And the only way to be sure whether it's a dynamical model instead of a screw up, so it's about 3 times out of 4 it's a dynamical model, is we're going to copy it. Oh, I didn't do it right. We're going to copy. So let's take a look. So we've made we have a set of state variables, and we got them started, and then we made rules to get from one row to the next. And now we're going to copy, I am going to make this a little smaller. And now we're going to copy them down. So all the machinery we did to calculate time step 2, we're going to remember to copy it. And then we're going to paste it. And, that's interesting. So we go for a while, and oh no, this is good. I see. I thought we ran out of susceptibles, but we don't. We run out of infectious individuals, but we don't run out of susceptible individuals, right? And this shouldn't be a surprise, because once we have a certain number of susceptibles, once the number of susceptibles gets low enough, then we expect the number of infected individuals to decline. And as the infectious individuals disappear, they stop affecting the susceptible individuals. So this looks pretty good. Let's see if we can visualize it, because that'll give us a better idea of what's really going on. Oh, I have no idea what just happened there. So we're now going to say what? Insert chart. That looks good, right? I'm happy. Oh, well, no, I'm not happy. And then how do we make the chart? So let's get rid of this. I want to make the chart a little bigger. How do I do that? Move to own sheet. There we go. So I should mention, in case I forget to, next time I should mention this is all online. That little URL I gave you, tiny URL, MMED, whatever. You can look at this. I'm pretty sure you can look at it right now. And if you ever try to look at it and can't, then let me know. But this is really almost all there is to the simple dynamic model. You can make it this simply in a spreadsheet and still have time, hopefully, to finish your lecture. And there's a lot you can do. Now that you have this, there's a lot you can do. So for example, we can ask why we're left with 2 susceptibles, which is a small number out of 1,000, but maybe not as small as we would have expected. And we can try to play with the parameters and see about that. We can ask, when do we get an epidemic? When do we not get an epidemic? We can ask, why is this peak so spiky, right? The peak of infectives looks suspiciously spiky. And that also gives us a chance to test another way whether we did it right, because we can go back and try. Maybe it's spiky because we have a fairly coarse time step. And we should actually be thinking about the time scales of what we're doing. So we ran this simulation for 100 days and we saw about what it did. We also say people are sick for an average of about 5 days. So a 1-day time step seems pretty fair, right? Seems like you shouldn't be skipping forward too much. But we could also ask if it looks a little smoother, but about the same if we change it to half a day. So I do that, and voila. Oh, I meant voila, it would be updated, but voila, it actually looks quite a bit smoother as well. And here we get a nice picture of the epidemic track. And what we see is when we have a lot of susceptibles, the number of infectious increases. As we get fewer susceptibles, the number of infectious individuals starts to go down. And as the number of infectious individuals starts to go down, they eventually stop infecting people. What is R0 in this model? How could you tell? Can you tell from this graph? I thought I could tell from this graph, but I got it wrong. But how would you try to tell from this graph what R0 is? Okay, so here at the peak, on average, what's R effective? R effective is how many people an infectious person infects. So at the peak, R effective is about what? About 1. Okay. Who said that? Always Jeanette. Thank you. At the peak, R effective is about 1. And so how would we find out just from this picture what we think R0 is? Well, the answer is we would try with our eyes, which aren't very good at it, to go down and see what the susceptible number was, right? So if, well, I'll give you the wrong answer because that's what I got, and I'm reasonably smart. It looks like there's about 250 susceptibles here, and it looks like there's about 1,000 susceptibles here. So I would say if R effective is 1 here, it was probably about 4 here. So that's my guess. Let's go back to the chart and see if there's another, the sheet, and see if there's another way we can calculate R0. R0, which has no units, but I'm still so nervous about units, I'm going to indicate that. How am I going to calculate R0 from my model parameters? Yes?
By just taking beta and then divide it by
Beta and multiply by?
multiplied by t.
D. I did not hear you say D. Okay, so R0 is in fact not 4, but 5. I guess that was an okay guess on my part. But this is good guidance too, and if you want to take this spreadsheet and you can play with it and see what happens, for example, if you make R0 less than 1. You might find it hard to get anything interesting to happen, but you might find a way. Or you can see what happens if you make the time step long, and you can get, by the way, insane dynamics that have nothing to do with diseases. I know none of you are mathematicians, but if you make the time step is reasonably short, this is a reasonably good disease model. If it's not, it isn't necessarily a reasonably good disease model.
So, sorry, could you review? We just need to multiply what?
Oh, I'm sorry, I meant to review that. Yeah, so Emmanuel correctly said beta times D. And remember from the conceptual model, beta is the rate at which I'm making potentially infectious contact. I'm making effective contacts. And D is the duration, right? So the number of effective contacts I make is beta D. And then the other thing that comes into that is that not everybody's susceptible or not everybody's infectious. But if we're calculating R0, that doesn't come into it. Thank you. That was an important clarifying question. No. You don't say, what? No, thank you. Yes, and we all have jet lag, or most of us have jet lag, but that's fine. Okay, so that's really what I wanted to show you. Oh, and the last thing I want to emphasize is that the ODE, we're not scared of ODEs anymore, and in particular, the ODE is exactly that complicated. If I had God's computer instead of my computer, I would just set the time step to be 1 over infinity, and this is exactly the ODE. Right? There's no difference. There's nothing in there. There's nothing weird or scary. This is the conceptual model. The simplest conceptual way to implement it is the ODE. The simplest practical way to implement it is this, which is something with a small discrete time step. Okay, so this is stuff that we'll go over again tomorrow. Julie will go over in more detail. But the ODE, converting our conceptual model into ODE makes some assumptions. It assumes that everything changes very smoothly, right? And that everybody knows what proportion of the population is infectious or susceptible. So I like this as an analogy, even though most people don't recognize it. Does anybody know what this is? This is a really cool thing. So this is a beaker, and it's got a little magnetic lozenge in it. And that's a magnetic plate that's spinning it around. So this is a chemical solution that's extremely well mixed, right? Within a few seconds, every molecule is going to be in the vicinity of every other molecule. And it has a lot of molecules, right? So if I was modeling this system, an ODE would be great, because it's got 10 to the 24th molecules, and they're well mixed, right? If I'm modeling Cape Town, it seems like a big city, but it does not have 10 to the 24th people, and they're not well mixed, right? The people who meet today are probably going to meet tomorrow, and probably going to meet the day after tomorrow. Oh, I need to do some stupid technical stuff. Save recording. The recording has been saved. That's a little alarming because I have no idea where or under what name, but we'll worry about that when you all are not around. The other assumption, you were asking what I meant by D equals 5. Sorry, D equals 5 days. And what's your name? John. John, and I don't see your name tag. There we go. Ah, John, I remember you. Or I remember his name tag. I recognize cars, this is true. I recognize cars, including cars of people close to me, by the license plates rather than by the appearance of cars. I'm a very strange person. So D is 5 days, but in the ODE model, what that means, it's like a light bulb model. However long you've been sick, you're equally likely to get better tomorrow, even if you just got sick or even if you got sick many years ago. So it's not a very realistic model. The light bulb model, this instantaneous model, is the simplest possible model, but it's not very realistic. And it's really about Einstein, again, being as simple as possible, but not simpler. Sometimes these assumptions work okay, and sometimes they don't. My favorite analogy for thinking about the exponential assumption, many people make human disease models, including some of our models, where the human lifespan is exponential. So an exponential with a mean of 70 years means that 5% of everybody in these standard model populations lives to be more than 200 years old. Okay, so that's not a realistic assumption, but people have made very good and correct conclusions and insights from these models. So it's okay if there's something unrealistic in your model, but you should recognize what's unrealistic in your model and be prepared to question it when you need to. So that's rarely realistic, but sometimes okay, is what it should say. So I've shown you the spreadsheet because for many people that's a concrete way of building it. Tomorrow I'm going to show you something very similar using scripts. I feel if you're doing anything that's important and reasonably complicated, you're better with a script where you can read, so there's similar amount of content on this screen as this screen. But this screen, you can see it all at once, right? And there's no probability that there's somehow messed up cell number E37. So we'll talk more about scripts, and all of you have been having fun learning R. All of you did the quiz. I happen to know that's not the case, but anyway. Spreadsheets may be more intuitive for simple problems, and some smart people use spreadsheets for complicated problems. I don't recommend it, but if you do use spreadsheets, there's also best and worst practices for spreadsheets, which are worth looking into. So back to transmission. I like to think explicitly transmission is constructed from contacts and probabilities. Here's a contact. But if you think about a disease like flu, there's so many different kinds of contacts, right? These are toddlers. One of them has probably got snot all over him. And we could also have a contact where two of us are on the same bus together or the same airplane together. So it can be pretty hard to define how many contacts you have and what's the probability of each contact. And in practice, we usually try to estimate beta, which is the rate of effective contacts, without necessarily trying to break things into contacts. There are some exceptions. In the STI world, I still think we'd be better off measuring beta, but there's a real culture of thinking you know what a contact is in the STI world, and there's a certain logic to that. So STI means sexually transmitted infection, and the idea is that one act or bout of intercourse would be a contact. But typically we wind up just estimating beta and not worrying too much about P and C. And so Jeanette, we can also ask the question about how beta changes with population size. And that's the way I conceptualize your question about beta SI over N. So in my mind, beta is always divided by N, because in my mind, beta is something real. It's a rate, it's an average rate of contacts, and it has units of 1 over time. So how does that vision relate to the decompositions we've seen? Well, until now, Steve's model, my model, the population was constant. And so it doesn't really matter what happens when the population changes. But in my mind, I'm imagining the population could change, and that if it changed, beta might or might not change with it. So my beta is the actual rate, and I like to think about how beta might change if the population size changed. And there's two very common assumptions about that. The first is often called standard incidence, where we assume that beta doesn't change as the population size changes. Right? And if we assume that beta doesn't change, so we write this conceptual beta as, in terms of this mechanistic parameter, beta 0, then our equation is going to wind up looking very much the same, except now we've sort of specified that we don't think this is going to change when n changes. And the other very common assumption is mass action. So mass action is the idea that people are crashing around at random in an ocean. It comes from chemistry, right? In an ideal gas, if you have twice as much gas, each gas molecule is going to have twice as many collisions. But that's not how people behave. I mean, this isn't how people behave either. There's also some technical terms for this which I add because some of you might have heard them. But if we imagine that beta increases proportionally to n, then we get the other common formulation. So in my mind, both of these, beta 1 Si or beta 0 Si over n, they're both fit inside the same framework. It's just the question of what are you assuming about how beta changes when n changes. And once you say it that way, you're not limited to these two choices, right? You could try, if you had enough data, you could try to have a realistic function for how beta might change if n is changing. So remember that beta is the per capita rate. It's the rate at which an individual susceptible or an individual infectious individual is making contact. And so we probably don't expect, if we go from 100,000 people to 20 people, we probably don't expect that per capita rate to reduce by a factor of 5,000, right? It'll be smaller, but not 5,000 times smaller. And if we go from 100,000 people to 10 million people, we expect it to get bigger, but not 100 times bigger. And so something like this might be more realistic. And once you recognize, people see standard, it's either mass action or standard incidence. No, those are just example assumptions that we can understand and that we can generalize. And I think I've probably talked roughly enough about units. It's just to remind myself to make sure to talk enough about units. I'm not worried about it on this occasion. But I will mention that beta, one of the things I like about my beta is it has these sensible units. It's a rate. How fast am I charging around meeting people? And then we can say beta over gamma or beta d is unitless, and R naught, which we're comparing to 1, right? That's people per people, cases per case. That's a very useful thing too, to remember that your R's are meant to be unitless, and they should therefore be ratios of two things with the same units. And our standard incidence beta 0 is 1 over time. If you're going to use mass action or something like it, it's worth remembering that beta 1 has kind of weird units. And you should really be carrying those units around and thinking, trying to, well, at the very least explain them to people, but also think about what they mean to you. Good, that's most of what I wanted to say, but since we have a few more minutes, I'll say a few more things. So here I've now added to my little diagram in two different ways, and I call it closing the circle. So in both of these, we now have a way to get into box R, by which I mean box S. I think I didn't get coffee at lunch. I think that was a mistake. So does somebody want to tell me what this diagram on the top, what extra mechanism I've added to the diagram on the top? So I have infection, recovery, and what? And what's a disease that might have this? New person.
That could be from Kenya. It could be loss of immunity.
It is in fact loss of immunity. And what's a disease that has loss of immunity? Where that would be something important enough to include in your model. Okay, it can be somebody else if you're not ready.
Sort of the common cold, except I think it's actually a new virus when you get a new cold.
Sort of the common cold is exactly right, because it's not, but this is probably a pretty good way of modeling it sometimes, right? Or flu is the same, sort of flu. And people, I'm personally guilty of modeling flu this way because it gets the first order thing even though it's not right. Can people think of diseases that might really be like this? It's hard to think of it, well, yeah, pertussis is the one I was going to go with if nobody came up with something better. Certainly pertussis vaccine does this. I mean, that's known, but I think pertussis probably does it to some extent. Gonorrhea may do it. I don't remember. Sarah. There's so many people this year. Okay, and what mechanisms are shown in this picture?
So you're introducing deaths in the lower arrows.
Yeah.
And then the upper arrow in the S compartment, you're introducing bats.
Yes, that's correct. And that's the one Steve already showed you. And when I used to be a mathematician, we had some theorems about how these two systems differ. But basically, the short answer is not very much, right? And especially for real human diseases where the time scale of remaining in R tends to be very long. These tend to have the same effect, which is that they close the circle and they produce the kind of effects that Steve showed you. And one is that it's a tendency to oscillate. So there's an endemic equilibrium, which I should have mentioned, but don't, and I thank Steve. So there's an endemic equilibrium, and if you start with a lot of susceptibles compared to the endemic equilibrium, what you're going to get is a lot of infections. And as a result of a lot of infections, you're going to get less susceptibles, and when you have less susceptibles, you're going to have less infections, and if you have less infections, you're eventually going to get more susceptibles. And that's why it tends to oscillate. In these simple models, but not in the real world, these oscillations tend to be damped, and the intuition for that, I think, is beyond the scope of this lecture. But one interesting thing I'll add is that if you include even the minimum amount of stochasticity, and by the minimum amount of stochasticity, I mean simply the stochasticity that arises from treating individuals as individuals. And I think I talk about this more. I definitely have a lecture about it, but I don't know if I get to give it to you guys this year. If you want to treat individuals as individuals, you have to add a certain amount of stochasticity. You can't say if I introduce one person into this population on Monday, I know that they'll infect one new person on Wednesday, but not on Tuesday or Thursday. I mean, as soon as you treat people as individuals, there's a minimum level of stochasticity. And almost miraculously, there's a perfectly consistent framework that's roughly as simple as the OD framework. That is the simplest way to incorporate demographic stochasticity. And so that's what I did here in a population of 100,000. The natural tendency to oscillate combined with sort of the minimum possible amount of stochasticity gives you oscillations you can see, even on this scale. And of course, as Steve pointed out, in the real world, we have a lot of drivers, right? So we have the Earth is turning on its axis every 24 hours and going around the sun every 365 days, and people are following customs like agriculture and school, following these patterns. So in real life, you're always going to see oscillatory drivers, which are going to interact with these other oscillatory forces. So in summary, dynamic models are the bridge, and they're the bridge, I didn't say this at the beginning, in both directions. Dynamic models are the tool we use to try to understand how individual level processes can scale up and show us what we see at the population level, but they also work in reverse because we're observing data in more detail at the population level. So what might be the individual level process that produces the patterns we see in different countries? Dynamic models are the tool for that as well. They are the tool that links the individual single event scale to the population longer time scale. There are many ways to construct and implement dynamic models. You're not afraid of ODEs. You're not afraid of understanding them, and you're not afraid of people who tell you you should be using them if you want to use something else. The ODEs are not better. They used to be better because before computers, they were basically the only thing you could do. But you have a computer now, and you can do what makes sense to you, and you can intelligently question whether it's a good tool for your project. And not only are you not allowed to be scared to not use them, you're not allowed to be scared to try to understand what they mean, even if you can't solve them. Because really nobody can solve them anymore, if it's anything but the simplest ODE. Very simple models provide useful insights. For example, reproductive numbers and thresholds. So the idea that we vaccinate 80% of the population against polio might be enough to make polio go away. I'll tell you more. I wanted to tell you more examples, but I'll tell you more examples of that on Thursday. Diseases have a tendency for oscillation, and in the absence of seasonal forcing, these oscillations have a tendency to be damped, to get smaller and smaller. More complex models can provide more detail, but they require more assumptions and more choices. We start with simple models and we build, right? We want our model to be as simple as possible, but not simpler, so we understand the simple model. We may understand what's wrong with it and why we need a more complicated model. Thank you. I almost don't want to say thank you because it requires you to clap, and you really don't need to clap.
Can you maybe talk a little bit more about the stochasticity that you add in that?
Yeah. So the stochasticity, this is beyond the scope of the lecture, but it's fine. But the stochasticity you add is you take these rates and you just leave them alone. It's all conceptually the same, except that you treat them as probabilistic rates. So instead of everybody flowing at a rate of 1 per 5 days, each individual flows probabilistically, but with that rate. And so when you have an event, it happens probabilistically and involves one individual. And you can just do that. It's just that simple conceptually, and it's not even that hard to do on the computer. And so that's the minimum amount of stochasticity you can have. As soon as you say these 100,000 people are real people, and as soon as you say, now that I have 2 cases, tomorrow I might still have 2 cases, or I might have 3, or I might have 1, but I'm not going to have 2.37 like the ODE tells me. As soon as you say that, this is the simplest model you can have.